Good afternoon, everybody. This is Peter Griffith. Thank you for showing up for the webinar today. There are three of us that are going to address the ABoVE Science Cloud. This is an orientation for people who are interested in proposing to the ABoVE call, which was released in December in Rose's 14. The three speakers, myself, I lead the Carbon Cycle and Ecosystems Office. We will also have McInerney, who's the Data Services Lead, and Dan Duffy, who is the High Performance Computing Lead. We also have contributions from quite a number of people from the High Performance Computing Group, at Goddard, the Climate Model Data Services, and from the Carbon Cycle and Ecosystems Office. I'd like to recognize their contribution. This wouldn't have happened without them. So in the ABoVE solicitation, you will have seen that the Carbon Cycle and Ecosystems Office is identified as the implementation and management group for ABoVE, that we will be doing the support for field activities, science team coordination. We'll help the scientists involved with ABoVE with logistics, safety, risk management, with interactions with local and regional stakeholders. And the Carbon Cycle and Ecosystem Office is also providing cyber infrastructure for data analysis and data management, which we're calling the ABoVE Science Cloud. So the ABoVE Science Cloud is going to, or already is, combining high-performance computing with the data management and tools for analyzing and processing geographical information that will be needed for the field campaign. Specifically, in the ABoVE study design that was produced by the science definition team, we've identified observations from satellites, from aircraft, and in-situ observations. And our aspiration is to merge and put all of these sources of information into an analytical environment that will accelerate the science for ABoVE. This rather complicated diagram is one vision of the data management life cycle. This came out of an article from last year in Frontiers in Ecology and the Environment. We've annotated that to show some of our aspirations for ABoVE, where that we will leverage the Science Cloud capabilities, particularly in that sequence when we go from on the right side after the QA/QC stage, when we get into the analysis and description. With the Science Cloud, we will have the virtual machines for the analysis of the data, and also the assistance that the science team will need in order to create both the discovery and the use, and use metadata that we require to ultimately publish and archive the data. And I'll give you some examples of where we're already in that process. And during ABoVE, we have a strong intention to contribute to and extend existing in-situ networks. This is an example from the concise experiment plan. It shows a browning and greening trend across the ABoVE domain, and on top of that are flux towers that are contributing to Ameriflux. It's going to be very important during ABoVE that investigators participate collegially with these communities of practice such as Ameriflux, and I'll mention a couple of others, so that we can both use the data that are emerging from their curatorial effort and also contribute to and expand it. So some other examples across this region that are taking some of the core variables that were identified in the concise experiment plan are organizations such as CALM and GTNP for some of the permafrost parameters, borehole temperature and active layer thickness, and then some of the weather and stream data that come from the Weather Service or through the HADS system. We also will cooperate with purveyors of geographic information such as GINA in Alaska. And of course, I've got the ORNL DAC at the bottom as the expected final archive location. So in the above concise experiment plan, which you'll find on the above website, we have already taken a number of geospatial data products, and all of the figures that are in the concise experiment plan are online and available as web maps. You can access those either as web services or download the data as shapefiles or CSV, depending on what the data type are. So I encourage you to make use of that information, both in your proposals and in your research. I would like to call your attention. There was an extended discussion amended from what was originally in the concise experiment plan. You'll find that in the more about research areas for above. That's well worth your time to read. And also on the above website, you'll find that there are a number of investigations that are producing data products that they are, in some cases, already sharing with the community. Each one of these project profiles can be viewed to see the data that are available, and I'll save you some clicking around and let you know that Kevin Schaefer and Skip Walker are the first to be ready with data products that can be shared. The Schaefer profile, if you drill down into that, I'm not going to give you the URL because it's quite long and complicated, but if you click through from the website, you'll find these two contributions that are in the process of being archived at the ORNL DAC. There's a formal citation at the bottom there and a DOI that's been assigned by Oak Ridge. Those URLs I do not believe will resolve if you click on them today, but in the next couple of weeks, those will be published at the ORNL DAC. So congratulations to Kevin for being first out of the gate with this data lifecycle management. Also in the Skip Walker profile, on the left you'll see the description that we have on our website, and there's a link on that will resolve to this Arctic Alaska geoecological atlas that they are working on. They have quite a number of products that are already available for your use on that site, and they are continuing over the next probably 18 months to add to that. And this Arctic Alaska geoecological atlas is a joint effort with Skip Walker's team and with GINA at the University of Alaska Fairbanks. So in any case, as time progresses, we'll be adding to the data that are available through the above website here from these pre-above investigations. So next up, Mark, you're next, right? Give us just a moment to exchange the presentations, and Mark will give you some of the details.
Okay, good afternoon. My name is Mark McInerney. I'm the Cisco Data Services Lead. I'm just going to give you a little bit of a background on what specific, how do we forward here? There we go. So I'm going to give you a little background. So, I'm Cisco Data Services Lead, but I manage a group called the Climate Model Data Services, and we're just going to talk about, my primary message is to talk about how we're supporting the ABoVE group, the campaign. But first I'm going to give you a background, about 5-6 slides to give you a background of who Cisco is and what some of the players are specific to the ABoVE project, just to give you a little background. I do know that these charts are detailed. If those of you on the phone that had a chance to go through and look, my intention isn't to talk to the detail, but since I know it's provided, it gives you a chance to read it. I'm just going to talk about a lot of these primary detail.
Actually, Mark, I'll just interject here that all these presentations are available as a PDF on the Science Cloud link where you went in to register. So you can download that PDF now if you want.
All right, great. Thank you, Peter. Yeah, so that's when I display a lot of detail and I skip really rapidly through that chart. It's not part of my primary message, but I just want to let you guys know you can go back and read it for yourselves. So a little bit of background. So CISTO is the Computational Information Science and Technology Office, or CISTO, and we have two of the primary groups in CISTO. CISTO is larger than the two groups, but we have the NCCS, the NASA Center for Climate Simulation, which Dan Duffy will talk to next. And basically, just a quick bullet for that, it's system support and specific to the Science Cloud, which is for ABoVE. And that's feeding into the ABoVE technical component. Data management and application support, that's my shop. So we're the softer side. We don't do the hardware necessarily, but we do the softer side. So the Climate Model Data Services is really, it's a team of what I call science technical experts. We're not an IT shop per se, we're a science technology shop. And so my folks will provide access to data, data visualization, data distribution, data management tools, and service for ABoVE science users. And we deal in large or big data components. All right, so these are the next 4 or 5 slides. I'm going to go pretty quick, but here's some conceptual layers just so you can understand why ABoVE and CISTO have partnered together and why CISTO is providing, it's really NCCS. I say CISTO because that's kind of the parent group, but it's really primarily NCCS. But here's some conceptual service layers that we're dealing in, right? So we deal in, well, before I go down there, there's 3 primary groups that are involved here. Climate Informatics, NCCS, I mentioned, and CDS. And if you look at the graphic, this rainbow graphic, everything we do is core to data. We provide compute services over it, data services, analytics services, and then knowledge services. And I have a chart for each of these. I'm going to go fast, but you can get the idea of what it is each of these layers represents. So climate model data, again, the message here on this chart, on chart 5, is really just talking about the size of data that we deal with. So here's some sample sets, 5 petabytes for the nature run. As far as that goes, the Earth System Grid Federation, for those familiar with that, we've published about 94 terabytes. Just skipping down, we deal with Mirror Analytics Service, which I'm not going to go into detail here. There's a chart that highlights it a little bit more, I think, coming up, the next 2 charts. But that takes the 80 terabytes of mirror data. And then NGA data, or the Land Cryosphere Science, very high resolution. It's really commercial data. We're dealing with somewhere around a petabyte, but we have access to lots of petabytes. I'll just use that term generically. So we deal in large volumes of data. I've heard it stated, and Dan's the expert here, not me, but I think it's somewhere 37 petabytes of data just sitting in our coffers of various uses. So lots of data. That's really what our primary focus is around for system. So compute services, there is a Discover cluster. It's a high-performance computing environment. There it is, chart 6, for those that want to read the detail of it. I think this is a little dated. The graphics cards, I think, have been replaced with something different, but this just gives you the general idea. Climate Model Data Services, that's the group I lead. You can see it's obviously the data services layer in our conceptual model. It's basically large-scale data visualization, as I mentioned. We also provide DOI services and things along these lines. We have analytics services. We have a service called Mira Analytics Service. Not really relevant here, but you can see more about this at caas.net, Climate Analytics as a Service.net, if you want to go read more. This is just showing some of the work being done in the analytics service layer. Knowledge services, we'll see. That's next. So these are things like ontologies and different things that's really not relevant here. Why do we even show you that? I show you that because I think it's important to highlight, and I'm on chart 10, if people are thumbing through. I show you this to highlight that it's not, we're not an IT shop per se. We're actually, like I mentioned earlier, a science technology shop. IT is our underlying fundamentals, obviously, network, storage, compute, et cetera. But these are highly skilled individuals that help run day to day on this, and which is why it's a good partnership for ABoVE. Okay, so let's get into some of the ABoVE specifics about how CDS is going to support ABoVE. The first I want to point out, some of these things are going to become more clear when we talk about Science Cloud. That's Dan's presentation that he'll be giving. So I'm going to kind of set the stage a little bit for him to talk more about the architectural layout for this. But I wanted to first point out my role really revolves around the data. So I'm on chart 11. Especially for the pre-ABoVE work done, we discovered that there was a lot of common needs as far as data. And so instead of allowing each individual investigator to download data sets that other investigators will need, it makes more sense to have them owned by the system, the Science Cloud in this case, and to make common stage data sets. So scientists have direct use for these. They don't have to worry about locating this data and downloading them. Additional data sets can also be added. It's not really the CISTO, NCCS, or CDS's call on that. It's the ABoVE team and the science team that will be established, I'm sure, not the technical team. We just need to know what it is. And then we're going to put data management services over top of it. So we give you the technical component to interact with that data. So what am I talking about? So when the pre-ABoVE work, we established, looks like 4 specific data sets that were required that we staged. For example, Landsat, that's inside the Science Cloud. Surface reflectance, it's about 50 terabytes compressed, that is. And we're looking at a temporal coverage from 1990 to 2012 by the time the projects are funded. MODIS is in there. I believe it's circumpolar. It's data surface reflectance. There's also an 8-day surface reflectance composites, about 248 terabytes. MIRA's in there. It's based off geospatial reanalysis, 81 terabytes. We have METAR observations. There's in the requirements, there's requirements to stage weather data. We just gave a sample of multiple sources of weather data, and we process about 350 stations, which is about 38 megs per week. I have a series of charts on the NGA data, which is going to be pulled for study domain, and we're estimating it could be somewhere about 1.8 petabytes. There's a little graphic on the right. I like to show this because it gives some perspective. Why stage? And some people still may not understand why it's better to stage. I don't know how many people are going to propose to this. Let's just pick a number. Let's say 25 people. I don't know how close I am. I'm not part of that. But if 25 scientists all needed, say, MIRA, which is about 81 terabytes, you can look on this chart. Of course, it's small on mine. Oh, here, I'll look over here. So the average household has about 7.4 megabytes per second average internet speed. On the chart, I've highlighted that first one, which is more, 10. So if you were to just download the data, locate it and downloaded the data, it looks like it'd take you about 741 days, over 100 weeks, or 24 months. It's a long time. Now that's obviously slower than most, corporate shops, government shops, universities, et cetera. So there's others, but you get the idea. The idea here is it takes a long time for each scientist to gain access to the data. Since we know what we likely want up front, we'll stage it. Then you don't have to worry about downloading. You can get right to your science. That's really the message of that chart. All right, so obviously some science results will be generated. These are just 3 quick bullets to say that this is where CDS can help support your generated data. We can either provide you short-term distribution services, which I have a list of what those mean exactly in the next chart. Perhaps some of the data that the individual investigator is producing will be helpful or valuable to other investigators. Again, not my call, but if that's deemed relevant, then we will fold that data back into the Science Cloud and make it part of the core data set so other investigators can have access to it and use it. So it's kind of a feedback loop. And one point on the third bullet, I just want to make sure is really the Science Cloud is not designed to be a long-term archive. That's really the DACS, ORNRL, others, but we can provide short-term. Relatively, it could be a couple years. I don't know. We have to talk about exactly the level of short-term that is, but it's long enough to support an active Science Cloud. All right. So this chart 13. So these are the common data distribution services that the CDS group supports. We have Common Web Access, FTP, we got it. There's the GRADS server, the Live Access server, Thread server. Earth System Grid probably won't be required here for ABoVE, but we support it. And then there's WMS services. I just highlight this so if at the end of work being done by an individual investigator, if they find there's some science data that needs to be made access more publicly, or again, fed back into the Science Cloud, here's the tools that we can offer to support you with, and we're here to do that when ready. So in that list, that's our common list that CDS actually supports. We do have Esri tools, ArcGIS, server, portal that we do have installed in the Science Cloud. It is something we're supporting primarily for ABoVE. That's why it's not in the main list. And right now, my understanding is there's really two uses for it. Use one is ArcGIS services for the carbon cycle ecosystem office to use as they see fit. I know Peter had a chart there in his presentation that has pre-staged some specific data that's out there. This is the type of stuff that they could use for it. We do intend to use that platform to display and manage NGA data, which I have some charts on here, the last couple of slides here after this. And then, of course, if the individual investigator needs ArcGIS services, it's there for them as well. So we have it installed. We're going to be the admin or application layer for it, allow access to it, and go from there. All right, so the last few charts are really highlighted specific to NGA. I don't know where everybody is on NGA data. However, this is just to give you a brief overview. So NGA is obviously National Geospatial Agency. It's unclassified data, and Digital Globe is the vendor. And basically, it's a pretty exciting opportunity. So NASA and other government-funded agencies have been given license to access this data, and there's about 4.2 billion square kilometers of data from 2000 to present that's available to access. There's 5 different satellites. You have WorldView 1, WorldView 2, ICONUS, QuickBird, and GeoEye. And there's a little bullet down at the bottom. WorldView 3 is coming online, and when that does, that will work to get that data available. It's just not there now. So really, this is sub 1 meter high-resolution imagery. If you're not familiar with it, it's pretty exciting. And the third bullet there, it's no cost to NASA or NASA-funded projects. I heard one calculation done that by the time we're done with this, we could be pulling up to $5 billion worth of data at no charge to NASA. So it's really an exciting opportunity here to have access to this data. Okay, so 3 primary goals to support NGA was really obtain, stage, and access. So what do I mean by obtain? So really there's partnerships been established. There's been a lot of work going on behind the scenes. Peter and Liz, myself and Dan and others, building strong relationships with not only NGA, I've been over there a couple times, Digital Globe, the Polar Geospatial Center from University of Minnesota. If you're not familiar with them, they're the largest holder of NGA data outside government, and of course NSF, who funds them heavily. So we have built those relationships. Agreements have been put in place. Processes have been put in place to order, retrieve, download, store ultimately put in a data management environment for you, the investigator, to have access to this data to do your work if you need it. It's there if you need it. So that's what goal 2 is. I kind of highlighted stage it. Again, we talked about the common environment to stage data. So NGA will be folded into that as well in the Science Cloud. So really the access for this data will require Science Cloud access. We're not just going to move this vast amount of data, which I also will mention that it's restricted data. You have to sign a form if you do need it. It's a loose form just saying you won't distribute it and that you'll use it for the work intended. But nevertheless, it's in the Science Cloud. That's where it has to stay to be accessed. I guess I already mentioned number 3, really, just having access to it somehow, which large, vast amounts of data. You have to know what you're getting towards your specific domain and have it presented to you. I love this image, too. This is Paul Moran, who leads the PGC Polar Geospatial Center. This is actually his camp at Bull Run Pass as a QuickBird 2 image in 2009. I zoomed in on the actual camp where they were staying. Gosh, you know, he has a funny story about this. I don't remember what it was, but there's a reason why they're spread out the way they are. But nevertheless, you can see the high quality of this image. So again, ABoVE has some specific NGA needs. So this is just a quick summary of what they are and some of the agreements we've established and the access we've have gained. There is existing imagery for Alaska and entire north of 60, entire northern Arctic North 60N, 60 North, because this duplicate there, already tasked by NGA, and we have that in stereo, panchromatic, and multispectral. And those are basically at PGC, and we have an established connection with them to go ahead and start pulling this data, and we've pulled 50 terabytes already from them just in the last couple of weeks, and we have that data. The data that's not in the coffers already, and NGA doesn't have, we actually have the ability to task. So we will get that core and extended domain tasked, circumpolar. Might take up to 3 years, 2 to 3 years to do, because we are obviously competing with an intelligent satellite that has other purposes. But we have access to task and get what's required for the agreement established for the above. Bulk transfers, the files are in NTF format. I already mentioned we have an ordering process. It's pretty slick. We know which domain we want. We process those. We have a direct network connection to NGA. No small feat to get a direct connection to NGA, the intelligence community, from a science community. We're pretty excited about that, to be able to pull the data routinely. There is an agreement to add value-added NGA imagery. These are things like, 0.5 meter panchromatic orthorectified Arctic mosaics for ABoVE, for the core and extended domain. So it's not just pulled data, there's a little bit more that can be added there. And of course, we talked about elevation models that will be provided from the raw data. And just as a heads up, this is just first pass. It's really using the AIM stereo pipeline. First pass meaning that it's not ground truth necessarily to vegetation, structures and things of that nature, but it will serve as a good first pass. So my time is almost up, but so I have 2 more charts here. This is just an image that shows the collection for the last 11 months of NGA, DG, Digital Globe is the vendor obviously, images at PGC. There's a lot. I wish I had the numbers of what this is. My hunch is, I think my last memory of it, somewhere 3 or 4 petabytes. You can see in the dark pink, it's less than 20% cloud cover is the quality of the image. Kind of small on my chart. The lighter pink is 20% cloud cover or more. That's for stereo. And then mono, it's the green is less than 20, and I guess it's a white or lighter green is greater than 20%. So there are some quality of imagery based off cloud, but our goal in getting the best images is really under 20%. And when an image comes in, some analysis is done on it, and then it's determined if it should be kept or tossed and reordered, or retasked for that matter too if needed, to make sure we have quality data sets. Mark mentioned that we will, or mentioned that we're going to have. Right, so that's this. Yep. So Peter was leading into my next chart, so he's right on task there. So really what we're pulling in is the core and extended region domains for ABoVE, and this is what you see here. Just want to mention that this was this is a highly zoomed in graph. It looks like we have all of Alaska. If you were to zoom out, you would see there's a lot of gaps in this. We're routinely pulling the data. Obviously the solicitation just went out, so we have lots of time to continue to grab the data. From an investigator side, from the technology support team, we're working hard to make sure we're filling that gap as fast as we can. It says greater than 100 terabytes for the ABoVE domain. We actually have around 61, but I guess it says in January, so my team has a few more days to get the other 40 to make this chart valid, as I smile. I already mentioned that zoomed in. So if you were to zoom into Alaska, you'd see the gaps, which you don't see in this image. But it gives you an idea that work has already been underway. We've pulled a lot of the data already, and the stream just continues to flow. I think that was my last chart. Yes, so if you have any questions, I think we're taking them or... Oh, okay. Okay, stand by here. It's too small for me to see. Oh, at the bottom. Okay. Great. Okay, so I'll read the question too so I can read out loud. What are the data sharing limitations for sharing NGA data with our research partners if we are funded by NASA? So here's, I think what I'll have to do is follow up to get the specific licensing agreement that we've established. I can tell you that in its high resolution form, you cannot share it, but there are some lessened restrictions if you were to have a lower quality image to share. And I think Peter's walking up.
Yeah. So data products that are created by the science team using the NGA data can be freely distributed to anyone, and we intend to treat them like any other NASA data product, that they'll be archived and publicly available to everyone. The underlying raw imagery needs to be treated according to the details of a fairly lengthy, it's about a page and a half, I guess, document that each investigator will have to sign. Collaborators who are directly involved in the NASA-funded research are welcome to participate in the analysis on the cloud.
Right, and just until anybody can have access to or lay eyes on the data, NGA has required us, and the legal team here at NASA has required us to have you sign the form. Basically, to summarize the form, you're not going to send out that data to anybody else who hasn't signed the form. So it's to protect the digital globe and NGA. Are there any other questions for me? Otherwise, I'm going to have Dan come up next. Thank you.
Before Dan starts, I'll address that. There's a second question, which is, has the cover map been filtered by season of acquisition? And that was not. That was all seasons. And the first pass through with this data, we're focusing on getting an image somewhere regardless of season. And as time progresses, then we'll fill in the seasonality of things. We realize that for a lot of questions, it's very important. Domain-wide, wall-to-wall, I think it's unrealistic to think that we'll have seasonality, immediately. But a few years into the project, I think we should have full seasonality in most locations.
Thanks, Peter. Thanks, Mark. So my job, I'm Dan Duffy. My job is to explain sort of the ABoVE Science Cloud capabilities to help you guys with your solicitation, with your proposals. All right. Of course, now I have to figure out how to advance. I can just use this. Yeah. Real quickly, as background, similar to Mark, I'll give you a couple of background slides. The NASA High-End Computing Program consists of two groups. One's at NAS and the other one here is at Goddard, and I lead the NASA Center for Climate Simulation here at Goddard in Building 28 in 606.2. So we are a part of science here. It's funded by the High-End Computing Program Office downtown by Dr. Sundar Lee, who is also the special interest lead within NASA for weather. As a high-performance computing center, we do the typical HPC stuff. So high-end computing, data storage, networking. We have lots of petabytes of data, as Mark talked about. Lots of model data, lots of observation data in there as well. What I'm going to focus most of the talk on from this point forward, after a couple slides, is the High Performance Science Cloud, which we've changed the name to the Advanced Data Analytics Platform, or ADAPT. Really, what you guys should on the phone worry about is the ABoVE Science Cloud. Our primary customers are most of the climate scientists, the GMAO and GIS, and as I said, we're located here in Building 28, and we like to think of ourselves as enabling high-performance science. A typical HPC application will, as you guys know, hundreds of thousands of lines of code. It takes small amounts of observational data input and creates large output. These are forecast runs. These are models. These are global climate models. These are WRF models, regional models, things like that. We have a very rigid HPC environment where users have to port their applications to the HPC. You have to understand which the operating system is, the tools there, the batch queuing system, and share that resource with quite a few other people. There's an example here of the GEOS5 nature run, what the GMAO is doing right now. They have a 2-year model that's running, and it has been run right now at 7.5 kilometer, basically 7 kilometer resolution. Generates about 4 petabytes total of data. They're still going to do the 3.5 kilometer at 3 months. We still have that to do. This is being used for these observing system simulation experiments, OSSIs, to help us understand better the additional observations that one needs to do on future platforms to make for the climate, to better understand the climate. And the data is all publicly accessible. As Mark said, FTP is there, so if you guys want to go to that website and download 4 petabytes of data, feel free. You can go ahead and start now. Might take you a while. So HPC solutions here are capable for you guys. They're capabilities that you guys can propose to for these projects. There's, as Mark said in his slides, I haven't updated the website, Mark, so there are petaflops of computing. We're over 2 petaflops of computing now, many petabytes of HPC storage. The NCCS has a full suite of services. There's help desks, there's ticketing systems, there's application support, all that stuff. You can get more information on our website. So that is available for proposers. We've been trying to do analytics support or analysis within the HPC system for a long time. All of the HPC centers are doing this. But we've tried to bootstrap the analysis in there. And what we found is the analysis tries to cut through the data in a variety of ways, as people on the phone know. You have to look at data in different ways, and I can't predict which way you're going to look at the data. And you can't sometimes predict which way you're going to look at the data. So sometimes HPC resources are not adaptable enough. They're not flexible enough to be optimized for analysis. Analysis is, as you can imagine, takes large amounts of input, be it model data or observation data, run it through hundreds of lines of Python code or IDL or MATLAB or some custom code, and generate just a little bit of data, generate an output, generate a picture that I've shown on the right here from Mark Carroll, where he's looking at decadal water predictions across the study region. Here is the Beaver Hill Lake area, and you can see the differences between Landsat imagery from 2000 to 2010, quite a big difference. These are examples of analytics, analysis that we expect. There's going to be a large amount of Landsat or MODIS or other types of processing that need to be done, and we need an agile environment to do this. So we stepped outside of HPC and we created this high-performance science cloud, or ADAPT system. It is side by side with our HPC environment. It's a lower barrier for entry. There's customizable runtime environments, meaning we're going to ask you what type of system do you want to set up. Is it going to be a Debian Linux system or CentOS Linux? I'll show you some software later. Basically, the way we're doing this is we're reusing a lot of the HPC hardware that we are actually decommissioning, surrounding that HPC, or actually embedding data within that HPC environment. So it is that, what Peter said, is the combination of HPC technologies and cloud technologies. These are virtual systems. These virtual systems can run these persistent data services that Mark talked about, ESGF, ArcGIS, OpenDAP, and things like that. But they can also have purpose-built science-specific images that are itinerant. So supposedly you need 48 images to run across Landsat processing, or you need a dozen images to do MODIS or something like that. We can set that up for you. The performance of the system comes pretty close to matching HPC levels of performance. There's very high-speed interconnects. There's high-speed connections network-wise to the cloud as well. And we can do management of rapid provisioning, firing things up quickly and taking them down quickly. So as we talked to Peter and Mark and others about this, we began to generate, let's peel off a part of this. Let's embed an above science cloud within this ADAPT system. And that's exactly what we did with the partnership with the CCE and CISTO and the NCCS and the Climate Model Data Services, is we basically have said, okay, let's set aside some resources for the above research to use this as a way of doing large-scale data analytics, as a way of doing their data management for both large data as well as small, diverse, large data as well. System components are typical what you would see from an HPC environment. There's these persistent data services where we can set up a data service that might be specific to a research project. Mark talked about many of those. We have database nodes, and sometimes various research projects need a high-performance database, and we have database nodes with solid-state disk environments in there that we can set up specifically for a project. Remote visualization, we have the capability of doing this. We're still working through some of the details of remote viz. High-performance compute, we talked about hundreds of nodes there, soon to be more. And then, as Mark also talked about, petabytes of storage. Now, I can't promise you that all 3 petabytes of storage are going to be available for above, but there are large storage repositories available, and we can work with you on provisioning that. Software-wise, open source, basically. Let's talk about, that's where we would like to focus. There are some commercial tools in there, but we like to primarily do open source, Debian, Linux, CentOS, Windows. We do have Windows. Yes, we do Windows. There's some commercial tools. Some of the best compilers out there are the Intel compilers. All of our chips are Intel, so those work well together. IDL, we have just a few of those. We like to focus on the open source tools of Python and NetCDF and any other things that you guys might have that bring to the table. Who installs the software? Well, you can install it in yourself in your home directories or no backup directories, but we can help you install it as well and configure that software in your virtual machines. We can also reach out to external license servers that you may have. This takes a little bit of time poking holes through the firewall, so that's the thing that you have to worry about, is just how long it takes to poke holes, not through our own firewalls, but through the C&E firewalls, and it typically can take weeks of time to do that. It's all paperwork. This slide here talks about data currently in the cloud, and Mark has different numbers. It doesn't matter which numbers are correct. It's a lot of data. Hundreds of terabytes of Landsat, MODIS, Mira data, which is the 50-kilometer reanalysis data from GEOS 5. Mira 2 is going to come out here very soon, and it'll have aerosols in there as well, and we can put that into the cloud as well. And that might be of interest to the study areas. NGA data, Mark talked about that. Additional data sets can be moved excuse me, into and out of the cloud, and that depends on what's funded. So ownership and management of these large data sets will be a shared responsibility. Sorry, misspelled shared there. It's a shard responsibility between us. That's my English coming up, my shard responsibility. It's not good. You don't get laughter over the phone. So, whenever he's muted. The shared responsibility between us and the science projects above and the actual scientists themselves. So if you say, well, I need this data set and it's 100 terabytes, and that's a funded project, that we can say, do we have enough data space? Let's go get it, let's download it, let's make it and into a shared area so everybody can get to it as well as the researcher can get to it. When you get access to the cloud, we're going to ask you these types of questions. This is just to set your expectations. We're going to be asking you, okay, what's the operating environment? What's the number of cores, the amount of memory things? And we'll sit, excuse me, I'm battling this cold. You will sit down with you and we'll walk you through all these things before we start firing things up. What we're going to find, I think, and what we've already found, is we typically already have images ready to go that you can use. So what works best in the cloud? Okay, if you're thinking about using MPI, the message passing interface, if you're thinking about writing a model with MPI, then let's move you to the HPC environment. It's not really designed for that. It can run that, but it's not really designed for that. It's more designed for inherently parallel processing of big data. So independent processes running side by side, looking at large data sets. You have to analyze Landsat. You want to, have 40 processes looking at different Landsat images side by side or NGA images and stuff like that. We have tools that can assist you in submitting independent parallel scripts across multiple virtual machines. We have tools by which we can publish the data. through these persistent data services, and that's what Mark talked most about. We've mentioned this several times. I don't want you to think of the Science Cloud as an archive. You're going to have to submit a data management plan with your proposal. We're going to adhere to that data management plan and get the end results over to the ORNL DAC or others. Itinerant large data stored in the system is going to be stored for the life of a project. What is that project? Is that project ABoVE, or is it a project that's a specific funded ABoVE research project? It could be either one. Landsat's probably going to be there pretty much through the life of ABoVE. But some MODIS data, for example, maybe the surface reflectance, or maybe somebody else is proposing something different that might need to get in there. That might persist for the life of a funded project. So it might be in there for 6 months or a year and might go away. The nice thing is that that's not the definitive copy of that data. And if another research project comes back and says we need that, we can go download that data again and get it there. We'll work with you and the ABoVE team and Peter and his team to make sure we're doing this the right way for everybody. Which brings us to the moving data. Mark talked about this as well. We can help there. We have high-speed access into the Science Cloud, 10 gigabit Ethernet out to the external networks. That what it typically ends up being is there's a bottleneck somewhere in there that we have to work through, and it's typically not our bottleneck. It's out there in the external community. But we can do this. We can do this in parallel ways. We can synchronize data and just download data automatically, set up cron jobs to do this. We're really pushing public data at this time into the cloud. We don't want non-publicly releasable data in there. Now, NGA is that special thing. It's kind of sensitive. We don't have the right to distribute it, but we have the right to use it. So how much storage can you use? We want to keep your storage small. So home directories and scratch space are relatively small, terabytes of size. So when you say, well, how can I propose a 50 terabyte data set? Well, that's fine. That's a shared area. That's not your area. That's a shared area that's owned by ABoVE and you and the system and managed by all of us together. So for the life of your project, you say, I'm going to need 50 terabytes and I'm going to analyze that we can get that in there, provision that, set it up so not only your project can view that, but other projects can view that. And that might be a publicly accessible data set somewhere. And then we'll keep it there and for the life of the research, funded research, or even longer. So think, again, small data storage for you. You're going to use shared storage space, large shared storage space to create, again, small amounts of output. That's what science is. We're going to continue to expand the Science Cloud, the ADAPT system. There's more compute nodes coming online, more services coming online. Yes, we are going to go get more Windows licenses. ArcGIS runs on Windows, so we need more Windows licenses, and there's demand for more Windows elsewhere. Remote desktop is something I want to try to push more and more. That's a maybe right now. And then ultimately we're going to get to a self-service portal where you can log into a portal and provision your own images. I want this image with this many cores and this much memory and these data sets. The people that do the real work, besides I don't really do any real work anymore. System engineers and system administrators that were mentioned before, Hoot, Scott, Garrison, Ramon, Brittany, and there's our help desk if you need more information. So that's all the slides I have. Real quick run through of the capabilities of the Science Cloud. Peter, we have a question. Science Cloud. See, Peter doesn't even know what ADAPT is. I'm changing the name on him. It's ABoVE Science Cloud.
Oh, you've changed. So the question is, once investigators are chosen, will there be a limit on how many users of the computing cloud will access to the Science Cloud be limited to a certain number of ABoVE users? And the intention is that everyone who's a member of the science team will have access to the Science Cloud. Don't believe that we're hardware limited, according to what Dan has told me.
Generally, I would say not hardware limited. We are going to have to schedule people a little bit, okay? What we found is that with research projects like this, there's an up and down. Everybody's on different paces. So we typically haven't run into a huge amounts of resource contention because we can schedule people, well, I'm not ready for this until next month, and so we can ramp up other people. So we'll help schedule. Mm-hmm. If we become resource contended, we'll help schedule. You're welcome.
So that we that's it for the prepared material. So if you haven't already figured it out, there is this chat window where you can pose questions. If you're listening on the phone and you're not online with the chat window, you can press *6 and ask your question, and then press *6 again to mute things. So our details available in the Landsat data currently in the cloud. There were some details that were provided in the presentation. I think we have to write up I will prepare a written response to that very excellent question, and we'll put that on the ABoVE website in the same page where you registered for this webinar. Not seeing any other questions at the moment. If there are further questions, they should be addressed to me, peter.griffith@nasa.gov. I will compile questions, will transcribe the questions that were asked during this webinar, and prepare a thorough answer to each one of them. They'll be publicly posted so that everyone who's interested has access to the same information. All right. Seeing no other questions, thank you very much for your attention this afternoon, and look forward to working with... Oh, there's one more. Hold on. It was to thank you. Good afternoon, everybody. Goodbye.